Hey everyone, how's it going? In this video, I'm going to talk about, in my opinion, an underused function on most thermostats, the remote sensor function. Better yet, on how to implement remote averaging sensors. What's this voodoo I speak of, you ask? Well, let me tell you. But first off, let me cover the remote sensor function. With most HVAC systems, the thermostat is located on a wall or pillar in an area near the return grill for the unit that it's connected to. In a regular built-in home, the thermostat should be mounted at 60 inches to center or 152 centimeters AAF, which means above finished floor, and 48 inches or 121 centimeters centered for ADA. ADA is American with Disability Act, which is for buildings like schools, government buildings, and hospitals. With the traditional method, the unit is being controlled by a thermostat that is mounted in one location. The unit doesn't care about any other room that the unit serves, just the spot where the thermostat is located. Or when a unit takes care of a large open area, it is only sensing the temperature directly around where the thermostat is mounted. That's hoping that the installer installed it in the best location, not just the easiest place. Another problem you can encounter is when the thermostat is mounted in a public location that everybody has access to it. You get what I call fiddlers, people fiddling with the stat. People see a button, they just have to press it. Or in an office you get Chubby Chucky, who's always hot and sweating and lowers the AC. And then you get Smoker Sammy, who's always freezing from her outdoor ciggy breaks every 10 minutes. Sure, you can lock out the thermostat with hitting a secret button combination like a video game finishing move. You could also buy a clear thermostat guard that covers the stat like it's the Hope Diamond. Then people just become MacGyver whenever trying to adjust the temperature when the thermostat guard's installed. Man, it's hot in here. Billy, go get a binder clamp, 2 paper clips, and Bubblicious from Jill and HR and make it fast. Sure, that can deter people from messing around with it, but it's not impenetrable. Over the years, I've seen many people just rip the guard right off the wall. The best way to combat this is to use the remote sensor function. If your thermostat has the ability, you can mount the stat in another room, office, closet, or mechanical room. Then just run a wire from the new secure thermostat location to another suitable location in the space and just mount the temperature sensor. Nice and easy. It's also perfect for homes as well. You can mount the thermostat in the master bedroom and install the remote sensor near the return grill. Your wives will love that. Control from inside the bedroom. Or you can just splurge for a Wi-Fi thermostat and control the heating and cooling set points from your phone, but that's another issue for another day. In my opinion, a remote sensor setup is nicer, cleaner look with only a small sensor on the wall, instead of a giant thermostat. It's also less attractive to vandals in public places because it's less noticeable. In addition, with the remote sensor function, you can also hook up multiple sensors in different rooms, all wired together to report one average temperature reading of all 4 sensors. Now, you can't just hook up as many sensors as you want, as long as the total number of sensors equals a perfect square. Now, a perfect square is a number or integer when multiplied to itself equals a perfect square. For instance, 1, 4, 9, 16, 25, or even 36 sensors. But using 1 or 4 sensors is the most common method. So how does it work? What's reading the temperature? And how can 4 sensors read as 1? To answer all these questions, we need to start with the basics. Resistors. A resistor is a passive 2-terminal electrical component that implements electrical resistance as a circuit element. In electronic circuits, resistors are used to reduce current flow, adjust signal levels, divide voltages, bias active elements, and terminate transmission lines, among other uses. High-power resistors can dissipate many watts of electrical power as heat. May also be used as part of a motor control or in power distribution systems, or even to test loads for generators. Fixed resistors have resistances that are only slightly affected by temperature, time, or the operating voltage. Variable resistors can be used to adjust circuit elements, such as a volume control or a lamp dimmer, or can be used to even sense heat, like a thermistor. Can also be used to sense light, humidity, force, or even chemical activity. Inside the carbon composition resistor, or CCR, consists of a solid cylindrical resistive element with embedded wire leads, metal end caps, which the leads are attached. The body of the resistor is protected with paint or plastic. Early 20th century carbon composition resistors had uninsulated bodies. The lead wires were just wrapped around the ends of the resistive element rod and soldered. The completed resistor was then painted for color coding of its value. Now, modern resistors have a standardized color coding system of colored bands, each band representing a different value. You also have surface mount resistors. These resistors have a number printed on them, which is a code to stand for the ohm rating of the resistor. The first two numbers are the first two digits of the resistance. The third stands for how many zeros follow. For instance, a resistor with 330 printed on it would be 33 ohms. 33 and 0, which means 0 zeros. If you had 331 printed on it, that would be 330 ohms. The 3 and 1 representing 1 0. I will cover all types of resistors in another video with more detail. The special type of resistor we're concerned with is the thermistor. The thermistor is a temperature-sensitive resistor, which the resistance value changes with the change in temperature. There are two main types of thermistors: the negative temperature coefficient, or NTC, and the positive temperature coefficient, PTC. The NTC means that when the temperature goes down, the resistance increases, and inversely, when the temperature goes up, the resistance decreases. Thermistors have a different range, with the most popular being 10K ohm, or 10,000 ohms, which means 10,000 ohms equals 77 degrees Fahrenheit, or 25 degrees Celsius. So by using your multimeter, you can measure the resistance of the thermistor or sensor and compare it to a chart and see what the temperature is reporting. All modern thermostats use onboard thermistors as the temperature measuring device. So how does the thermostat function with the remote sensor? It accomplishes this by sending out a DC voltage from one of the remote sensor terminals, S1, down the wire and to the thermistor. It changes the resistance of the thermistor, lowering the DC voltage output to a lower voltage, which is based on the space temperature. It then travels back through the wire to the other remote sensor terminal, S2. The temperature could then be interpreted as the temperature of the space. This is also how most temperature sensors work in an HVAC unit mounted temperature sensor or temperature sensor in a building automation system controller. They are extremely common. Now that example is just one thermostat with one remote temperature sensor. Now let's say you have a unit that is taking care of a large open area or area with multiple rooms and you have temperature imbalances. Let's say there is one unit taking care of 4 offices, and the office with the thermostat in it is in the corner perimeter, so the temperature is always warmer than that of the other offices on the interior. This will cause the unit to run longer and overcool the other 3 spaces while it tries to satisfy the temperature of the office where the thermostat is located. So what can we do about this? You can install 4 temperature sensors, one in each of the 4 offices, wire them in series parallel back to the thermostat. The way the voltage travels through the circuit, it comes back as one resistance value, which is the average of the 4 sensors. Pretty cool, right? So what's going on here? Let me explain. When you test a resistor, motor, or other circuit with your meter sends a known voltage out from one of the meter leads through the load or resistor back to the other lead. That voltage then comes back to the meter. The meter can interpret that value and display the corresponding resistance value. That's also how your meter does continuity. It sends a DC voltage out on the red lead, and when it receives it back on the black lead, it powers a buzzer inside of your meter. Knowing that, you should start to get used to using the ohms resistance scale on your meter whenever you're checking motors or other coils, not continuity. Continuity is for switches and small distances. If you have a very large distance or a very big coil, continuity might not be powerful enough and may give you a false negative. You should always check motors with resistance, not just continuity. So back to voltage through a resistor. When you have 2 resistors wired in series, the resistance is equal to the values of both resistors, and the voltage going through the resistors drops according to each resistor. For example, if we measure the value between 2 resistors that are each 10,000 ohms, the multimeter will read 20,000 ohms. If the voltage going through that circuit was 5 volts DC, the circuit would be roughly 3.3 volts DC on the output. Now, if we put those 2 same resistors in parallel, what we are creating is called a voltage divide. Half the voltage source goes through one resistor, and the other half goes through the other resistor. Now our multimeter would read 5,000 ohms, or roughly 1.7 volts DC. So what do you think would happen if we had 4 resistors and put them in series parallel? 2 sets of resistors in series, then put those sets in parallel. The way to solve it is to take each set of resistors in series and add up their values. So for instance, 2 10,000 ohm resistors in series would equal 20,000 ohms. So we can treat them as one 20,000 ohm resistor. Now if we have 2 20,000 ohm resistors in parallel, our voltage divide would drop the voltage and our resistance would be read as 10,000 ohms on the circuit, just like we're reading one 10,000 ohm resistor. Now substitute the resistor for thermistors. So 4 10K ohm thermistors will act as one thermistor temperature sensor to the thermostat. But what happens is the 4 independent thermistor readings are different values based on the temperature of the space that the sensor is in. They all get averaged and report one temperature to the thermostat. The thermostat has no idea that actually 4 sensors are hooked up instead of just one. Implementing this on a problem job site could help the unit more evenly control the space. If this doesn't work, the only next option would be to upgrade the system to some type of zone system with dampers or VAVs. This is a cheaper method, but it is not a fix-all. Now on to the installation of the thermostat and the 4 averaging temperature sensors. Many years ago, I came up with a method for wiring in these sensors. It's the easiest way in my opinion. First, check to see if the current installed thermostat has the ability to have a remote temperature sensor added to it. Pop the thermostat off the subbase and look at the terminal strips. See if you see an S1 or S2 or T1 and T2. If it does, go to your supply house and pick up 4 remote temperature sensors for that model. If not, you might have to purchase a new thermostat like a Honeywell Vision Pro or something comparable. Now to plan the install. Pick a location to mount the thermostat that is a general easy spot to get to, like a closet, mechanical room, or in a manager's office. Then go back out and find the best location for each of the 4 temperature sensors. Once you have the spots picked out, scope out how you'll run the wire. Now above the location where the thermostat is to be mounted, either above ceiling tiles or in an attic of a home, that's where we'll mount the splice box. From there, run an 18-2 conductor down to the thermostat and label that wire T-stat. Then run another 18-2 wire to each temperature sensor location back to the splice box. Now label each wire, sensor 1, sensor 2, sensor 3, and sensor 4. It doesn't matter which is which, just as long as each sensor has a unique label on each end. Now it's time to mention that if you don't have some type of wire labeler, like a P-Touch, you should pick one up. They're extremely useful and have ones at all different price points. You should really be labeling your work, not just because it looks nice, because it'll also help somebody else in the future if they have to troubleshoot your work. I have installed these dozens of times, but every time I do, I print out a wiring diagram graphic that I made a few years ago and staple it to the wall directly above the splice box. It makes it easier to reference when you're wiring it. Just go wire for wire like the diagram graphic shows. Then you can just leave the paper on the wall at the splice box location, just in case in the future if someone has to troubleshoot the circuit, they have an easy reference. A link to the graphic I created is in the video description down below. Next, terminate the 4 sensors in the space and land the 2 wires on the thermostat remote sensor terminal on the subbase as indicated in the diagram. Then go into the installer menu of the thermostat, enable the remote temperature sensor function, selecting the 10K ohm thermistor setting. Now the temperature should be displayed on the front of the thermostat should reflect the average temperature of the space for the 4 zones. For some reason, if you're getting a wacky temperature like 100 or 20 degrees, go back and check your wiring and your splices. Make sure you didn't miss something or miswire something. Going over the resistance of the thermistors in series and parallel from this video, you should be able to use your multimeter to test the wires and the splice and know what values you should have. In a future video, I will cover resistors and other electronic components used in HVAC. There's not one unit that doesn't come out nowadays that doesn't have electronics and a circuit board in it. It's very important for a technician to understand these basic principles to help you troubleshoot and understands how units function. So I hope this video helps you out and enlightens you into some of the other options you have at your disposal to offer your customers. If you like this video, please check out my social media and other videos on my channel, and consider subscribing and hitting the notification bell, selecting all, to be notified when I upload. Thanks for watching, and I'll see you in the next one.